As we begin the topic on graph transformations, it's really important that we are comfortable and familiar with some of the most common mathematical functions. Pretty much anything your calculator can do is known as an elementary mathematical function, and we can describe an enormous range of different shapes and curves with combinations of those functions. But before we can get to manipulating them, stretching, squashing, turning, putting one inside the other, we need to make sure we're comfortable sketching those functions in their purest form. So I've got a few functions here that I'd like you to have a go at sketching for yourselves. I'd like you to include key details on your sketch. Don't worry about marking on perfect gradations along the X and Y axes. Don't worry if your X and Y scales are not quite in a perfect one-to-one ratio with each other. That's not particularly crucial. What matters is that the shape of the curve is roughly sensible. So if your curve has a positive gradient and is increasing at a certain point its gradient, then you need to have a curve that reflects that. If there are any crossing points on the X or Y axes and you can calculate what those are, you should include those on a sketch. And similarly, if you can find any asymptotes or any turning points, a maximum or a minimum point, then ideally you should include that on your sketch as well. So pause the video, see if you can come up with a sketch for each of these 6. And when you're ready and you've got your pictures, then unpause and compare to mine. Okay, for our first one, y equals x squared, the first thing to notice is that this will give the same values for positive x inputs as it will for negative x inputs. So your curve is going to be perfectly symmetrical about the y-axis. 3 squared gives the same answer as negative 3 squared. So this is what your curve is going to look like, a nice classic parabolic shape, the standard quadratic graph, and it crosses the x-axis and the y-axis at the same point, 0, 0, the origin, because 0 squared is 0. If you've included any other points, you might have the point 24 or the point minus 24 like I've got. For y equals x cubed, the curve will increase more steeply after a while. For small values of x, when you cube a number between 0 and 1, it makes the value smaller. But if you cube a number that's bigger than 1, it makes the value bigger, and it makes it bigger faster than squaring it does. However, when you cube a negative number, it remains negative. So cubing, or in fact any odd power, will preserve the sign of your input values. That means instead of starting high and ending high with a dip in the middle like x squared does, the x cubed graph will start low and end high. So it'll be coming up from the direction of negative infinity when we're looking on the left-hand side of the graph. And as we read across towards the right, it moves generally towards the direction of positive infinity. So something like this. In between, it flattens out because of what we were saying about cubing numbers that are close to 0. And at 0, 0 exactly, it crosses the x and the y axes. It might look like it crosses in other places, but it doesn't. X cubed has a triple repeated root. X equals 0, x equals 0, and x equals 0. So it crosses the x-axis only at one point, and that point is the origin. For y equals 1 over x, the first thing I notice about this is that it's not going to work everywhere. If x is equal to 0, then we're trying to divide 1 by 0, which won't happen. So there's a hole, a gap somewhere. And that gap manifests itself as an asymptote, which means everywhere where x equals 0 is going to be inadmissible for our function. Essentially, we can think of the vertical line x equals 0, in other words, the y-axis, as an asymptote. Our curve might approach that point, but it will never quite reach it. There's another asymptote that's a little harder to see, but if you think about what happens as x gets larger and larger, 1 over x will get smaller and smaller. But if x is still positive, then 1 over x is still positive. So y will be positive, but tiny when x is a large positive number. By the same token, if x is a very large negative number, like minus a million, y will be tiny and negative. So y is getting smaller and smaller as x is moving to the right, and y is also getting smaller and smaller as x is moving to the left. But it will have the same sign as x. The other thing that happens is close to x equals 0, y can get very large. If x is 0.1, y will be 10. If x is 0.001, y will be 1,000. And if x is a very small negative number, y will also be negative, but it will be huge. So we get this kind of behavior. This particular shape is called a hyperbola, and you might learn more about them if you do further maths. This particular one, we can see has asymptotes on the x-axis and the y-axis, and it has nice symmetry about the line y equals x. And that's because if you swap x and y, you get x equals 1 over y, which is actually the same equation as this one. You can rearrange it and turn it into x equals 1 over y. So if you take the reciprocal of a number, and then you take the reciprocal of your answer, you're back where you started. Y equals 2 to the x, the next one down here, is an exponential curve. This type of graph grows faster than any polynomial curve. In the long run, 2 to the x will always win when you compare it to x squared. And in the long run, it will always beat x cubed. In fact, because the power is what's getting bigger with 2 to the power of x, no matter how large the power is for your polynomial curve, y equals x to the 100, y equals x to the million, eventually any exponential curve with a base that's bigger than 1 will beat your polynomial curve. These curves look a little crazy, especially when you start zooming out and you realize just how steep they're getting. It's hard to visualize exactly what's going on as x increases because 2 to the x increases much faster than x does. If we look at 2 to the 10, we're already at a number that's bigger than 1,000, and 2 to the 20 is bigger than 1,000,000. 2 to the 30, we're now 1,000 times bigger again, so we're increasing by a factor of 1,000 every time x increases by 10. We're not just going up in regular steps or slightly more rapid steps each time, we're increasing by a multiplicative factor. Just like the spread of a virus, if the number of cases doubles every 7 days, then the graph is going to look like an exponential curve. And even if the number of people infected is very small initially, it doesn't take very long before the number of people infected grows to however big the potential population is. Key points on this graph: it crosses the y-axis at 0, 1. That's because 2 to the power of 0, or in fact anything to the power of 0, provided we've got a non-zero base, anything to the 0 will be 1. So all exponential graphs, y equals 10 to the x, y equals e to the x, they all cross at 0, 1. And then as you move to the left and think about what happens as x becomes a large negative number, numbers like 2 to the minus 10 or 2 to the minus 20 are still positive, they're just very small. 2 to the 10 is 1,024. 2 to the minus 10 will be the reciprocal of that, 1 over 1,024. So it's a very small number, but it's still positive. And no matter how far you go to the left, you're always going to be finding the reciprocal of a very large number. So it's always going to be a very small answer, but bigger than 0. 2 to the x is always greater than 0. It never touches the x-axis, and it never goes below the x-axis. So the x-axis itself, the line y equals 0, is a horizontal asymptote. But don't be fooled, there are no vertical asymptotes here. Even if the curve might look like it starts to become vertical, it never does. It's just growing faster and faster. Y equals root x should remind us of y equals x squared. It's in some sense the opposite graph. A more precise term would be the inverse function. It's a way of reversing the process of squaring something. So in the same way that a y equals x squared curve will increase at an increasing rate, a y equals root x graph will increase at a decreasing rate. So as x increases, root x also increases, but less and less quickly. For instance, you have to add 5 to get from 2 squared to 3 squared, but you have to add 21 to get from 10 squared to 11 squared. So you get diminishing returns essentially here. The curve increases relatively quickly at the beginning, but then more and more slowly as we go along. The other thing you'll notice is that it is only giving us positive results. Y equals root x refers to the principal square root of x. The principal square root basically means the one the calculator will give you. So if you ask the calculator for the square root of 225, it'll give you an answer of 15. Not 15 or minus 15, but just 15. If I'd wanted to include the negative square root, I'd need to graph that separately. Y equals minus root x. The other thing you might notice is that the graph doesn't exist when x is negative. And that makes sense as well. We can't square root a negative number. It's equivalent to saying the y equals x squared graph doesn't go below the x-axis. By the same token, the y equals root x graph can't go to the left of the y-axis. Now, y equals sine x is a periodic function. And if you're looking for roots for this function, you'll find there are plenty of them. The curve crosses the x-axis at 0 degrees, at 180 degrees, 360 degrees, and so on and so on. In fact, you can go backwards to minus 180, minus 360, minus 540, minus 720, as well as forwards as far as you like in jumps of 180 degrees. Every single one of those numbers will be a root for the graph y equals sine x. It has a maximum point at 90 degrees, and the maximum value it gives is 1. And it has a minimum value at 270 degrees, giving a minimum of -1. And again, just like the roots, those repeat every 360 degrees. So this one's a cyclic or a periodic graph. The next thing we want to look at is how we can sketch a mathematical function. So if we're happy with the general shapes of the functions we've seen before, now we start to look at some specific examples and how we can work through a process that will allow us to generate a sketch for a function that we've never sketched before. In this case, we have x cubed minus x. And to help us with that, I'm going to bring in a checklist that we can follow. So we're going to start by doing this. Consider the general shape. When you look at that, y equals x cubed minus x, you should already have in your head, hopefully, a few ideas, a few pictures of what that graph might look like. Because a cubic graph could look like lots of different things, but still, it can't look like just anything. There are a whole range of different possibilities for a cubic, but there are a few sort of classic types of cubic that you might expect to get. So it may be that it has a minimum followed by a maximum. It may be that it has a maximum point followed by a minimum. And it may be that it has neither a maximum nor a minimum, possibly a stationary point of inflection like y equals x cubed itself, where the gradient becomes 0 temporarily, but it never actually wobbles up and down. It might be that we have a non-stationary point of inflection, where the curve does have a wobble, but it never quite gets to a gradient of 0. So there are lots of possibilities, but the possibilities are not endless. We can categorize them, quantify them, and think about which one this one might be. The next thing we look for is intercepts. So we start with the y-intercepts. Are there any points where it crosses the y-axis? Generally speaking, for well-defined functions, we're going to find there is going to be one y-intercept at most, unless the y-axis itself is an asymptote. So we can find it most easily by substituting x equals 0, because the y-axis is the line x equals 0. If we put x equals 0 into this, predictably enough, we get 0. 0 cubed minus 0. So we know now that our curve crosses the y-axis at the origin. The next thing we look for are the x-intercepts, or the roots as we call them. If we set y equal to 0 and we solve the resulting equation, we can find all the values of x for which y is 0. In other words, all the input values we could put into our function which would give us a 0 output value. All the places that the curve crosses the x-axis. So that's what we've done here. We replace y with 0 and we solve. It's a cubic, but it's a cubic that we can fairly easily factorize because x is a common factor of both terms. And once we've pulled out x as a common factor, we've got a difference of two squares format. So we can break that apart into x plus 1 times x minus 1. Now we've got three separate terms that all multiply together to give 0. So there are three different ways to make that true. Either the first term could be 0, or the second term could be 0, or the third term could be 0. And that gives us roots of 0, minus 1, and 1. So now we know where it crosses the x-axis. One of those points is, of course, the same place it crosses the y-axis, but the other two are points on the x-axis that we didn't know about already. It's worth noticing at this point, if we'd got a repeated root, that doesn't just tell us that the curve touches the axis at that point, but it tells us that we have a turning point of some sort. So it might be a maximum point or a minimum point. It's a little bit like the graph going below the axis and immediately coming back above the axis, both at the same place. We'll see an example like that a bit later on. The next thing we would look for in general when sketching a curve is to identify any vertical asymptotes by looking for holes in the function. By that I mean, are there any values of x that would make the function break? Are there any numbers we could put in that the calculator wouldn't like? If we try doing tan of 90 degrees or 1 over 2 minus 2. If we find ourselves divided by 0, that's usually the classic way of identifying a vertical asymptote. But in this case, we've got a cubic equation, and there are no cubics that have any problems of this sort. You can always cube any number, positive, negative, 0, it doesn't matter. You can always cube a number, you can always square a number, you can add or subtract multiples of them. So if you've got a cubic graph, it's going to be well defined everywhere. There are going to be no points where the curve doesn't exist. The next thing we look for is the long-term behavior of the curve. This means what happens as x gets very big and what happens as x gets very small. So you can either think of an actual large value for x, or you can think a bit more abstractly. If I have a very, very large value for x, then everything apart from the x cubed term becomes pretty much irrelevant. For instance, if x is 1,000, then x cubed is going to be 1,000 cubed. Well, that's a billion. That's a lot bigger than 1,000. So even if you had a large number in front of x, eventually x will be big enough that the x cubed term is the only one that matters. So in the long run, we say that the x cubed term is the dominant term. It's the one that dictates the eventual behavior of the function as x gets larger and larger. So we say as x approaches infinity, which is just a mathematical way of saying x keeps getting bigger without limit, then y will also get bigger without limit. Y will approach infinity. And on the other end, because cubing preserves the sign of the input, in other words, if you cube a negative, you'll get a negative result, and if you cube a positive, you get a positive result. That means if x is a very large negative number, x cubed will be a very large negative number. And so our function, which is ultimately dictated by the dominant term for very, very large sizes of x, our function will also be negative when x is sufficiently large negative itself. The easiest way to say this is the curve starts low and ends high. So of all the different possibilities we could have for our cubic, we either have curves that start high and end low, they'd be negative cubics, or curves that start low and end high. In other words, as you read from left to right along the curve, you start with negative numbers. There may be a wobble in the middle, there may not, but you end up with positive numbers. This is one of the reasons we know for sure that there is always at least one solution to every cubic equation. At some point, it's going to have to cross the x-axis because it starts negative and ends positive, or it starts positive and ends negative. The last thing we would normally look for is any turning points. Is there a maximum point somewhere? Is there a minimum? And if we had a quadratic, we could complete the square. Once you've learned a little bit of calculus, we can use differentiation to identify places where the gradient of the curve is 0, and that would help us to pinpoint exactly where those turning points might be. In this case, we're not going to use calculus, but we can still see something of where they would be expected. We know what cubics look like, so given that this one crosses the x-axis at -1, then again at 0, then again at 1, we can be expecting, if it comes up from negative infinity, effectively, it comes up from below the x-axis, it crosses and then crosses again, there must be a maximum in between those first two crossing points, because it comes up and then it must be going down. After that, there'll be a minimum point, and then it will cross again as it goes back up. So this is the sort of curve we're expecting. Ideally, if you do a sketch for this, you would mark on the values that I've written down, but as long as they're labeled somewhere clearly in your work, it's not crucial to have it on the graph as well. But the crossing points we've got here are -1, 0, 0, 0, and 1, 0. And you can see the classic behavior of a cubic graph. It's got a maximum first, followed by a minimum. It starts low in the bottom left, in the third quadrant we call it, and it ends high in the top right, in the first quadrant. Now you should have a go at a few of the graphs from exercise 4a. There are loads of them, so if you want to try more than 2 from each of the questions 1 to 4, then feel free. Do as many as you need until you feel comfortable with the process, but try at least 2 from each of the questions 1, 2, 3, and 4. And then have a go at some of the later questions, the problem solving or exam style questions. In particular, I'd recommend questions 5 and question 7. When you've had a go at those, return to the video and we're going to move on to look at quartic graphs. So we already saw that cubic graphs can be more complicated than quadratics. There are more different things they can look like. Any quadratic could be stretched or squashed and moved so that it would match up with any other quadratic. But we can't do things as simple as stretching, squashing, and moving to turn a cubic into another cubic. There's just too much that might change. Some cubics have maximum and minimum points and some don't, for instance. Quartics have even more variation because there are more different things that you could change with a quartic. You can see from this animation that there's all sorts that they might look like, but in general, you can imagine a quartic as being a curve that has the potential to cross the x-axis 4 times. We're going to work through this example following the same kind of pattern we did before, so you'll see how the general structure of how you sketch a curve is followed in pretty much any example we have. So let's start by looking for the y-intercepts. We find the point where the curve crosses the y-axis by setting x equal to 0, because the line x equals 0 lies perfectly on the y-axis. Well, when x is 0, even though this is in a factorized form instead of an expanded form, it's still pretty quick to identify what number we're going to get. We just replace x with 0 and then we evaluate the result. Here we get -12. So now we know the y coordinate where the curve crosses the y-axis. The next thing we look for is where it crosses the x-axis. So this bit takes a bit more work. We have to replace y with 0, and that leaves us with a quartic equation. In general, quartics are hard to solve. Your calculator can give you numerical solutions to a quartic equation if it's written in a standard format. But if it's factorized, then your job is mostly done. All you need to do is take advantage of the zero product principle. If you've got a bunch of terms that multiply together to give 0, then one of them has to be 0, at least one. In this case, we've got a couple of brackets, x minus 2 squared. So there's a repeated linear factor in there, x minus 2. That means we get a repeated root of x equals 2. Because if we set x minus 2 equal to 0, we get x equals 2. But there are 2 brackets like that. The fact that it's repeated is important. We've got this idea that it doesn't just cross the x-axis when x equals 2, but it touches the x-axis and potentially we're looking at a minimum point or a maximum point. Depending on how repeated the root is, this could be different. So if you have a triple repeated root like you could get in y equals x cubed, then the curve may still cross the axis, but it would have a little bit of a wobble, maybe a point of inflection along the way. In this case, it's a double repeated root. I'm expecting a maximum or a minimum point at x equals 2. We've got another factor in there which has been left as a quadratic instead of being factorized into 2 linear brackets. And there's a good reason for that. It can't be factorized. Turns out if you try to solve -3 minus x squared equals 0, you get stuck pretty quickly at x squared can't be negative, so there are no solutions to x squared equals -3. Once we recognize that, that tells us that we found all the roots. We know all the places that the curve touches the x-axis. It only happens at the point 2, 0. Next, we look for asymptotes, but again, like we said, cubic graphs, quartic graphs, in fact, any polynomial graph is not going to have an asymptote because there are no numbers that cannot be squared, cubed, raised to the power 4. All of these operations that we do when we're substituting a number into a polynomial, they work fine for positives, negatives, 0, whatever you need to put in. So the last thing we start looking for is the long-term behavior of the curve. We want to know what happens as x gets very, very large and what happens as x gets very, very low. So for big positive numbers, for big negative numbers. The dominant term here is -x to the 4. you might need to expand out the brackets a little bit, but remember we only care about the most significant term, so you don't need to expand out the whole thing. You just need to look for what type of quartic it is. Is it going to be a positive quartic or a negative quartic? Because that will give you the key information. If x is very large, x to the 4 will also be very large, even larger. But if you put a minus sign in front, that makes it a huge negative number. So as x approaches positive infinity, y approaches negative infinity. As we move to the right, the curve goes down in the long run. But also, if x is a negative number, x to the 4 is still positive. And so if x is a large negative number, like minus 1,000, x to the 4 will be a very large positive number, like positive a trillion or a quadrillion or something. But when we put a minus sign in front, it becomes negative once more, which means that if x is either a very large positive or a very large negative, y will be negative. We can think of this more succinctly as the curve starts low and ends low. So it comes up from below the x-axis and it goes down below the x-axis afterwards. Whether it crosses completely or just touches or doesn't touch the x-axis at all, that's something we need to figure out by looking at the rest of the information we've generated. Last, we've got the general shape of what quartics look like, and we can figure out whether or not there's likely to be a maximum or a minimum somewhere. It looks like there'll be a maximum value at x equals 2 because we've got that repeated root. And because it's a maximum value, it comes up, touches the x-axis when x equals 2, and then goes back down again. It has to go back down, so it can't go above the x-axis, otherwise it would have to cross in order to get below it once more. Now we know we're dealing with a quartic equation, a quartic function which never goes above the x-axis. Once you've marked on the key points and you've got a sense of the shape, you should be able to construct something that looks a bit like this. Now, the details of the curve are not too crucial, so don't feel bad if yours looked a bit too symmetrical. This is not a symmetrical graph. It's an awkward looking quartic graph. But if we know that it crosses the y-axis at minus 12, and we know that it has a repeated root at 2, we can infer most of what's relevant and important about this curve, and our sketch should represent that. All the way through the curve, the gradient is decreasing. It starts out with a very high positive gradient, and throughout the curve, the gradient is going down and down and down. It reaches a gradient of 0 when x equals 2, and then becomes steeper and steeper negative as x increases. To try a few quartic graphs examples, I'd recommend you go to exercise 4b and try questions 2, 3, and 4. When you've finished those, come back to here and we'll look finally at reciprocal graphs. To help you, once you've sketched the graph and you want to see how close your curve was, you might find it useful to head over to geogebra.org or to use the app on your phone and see how closely your curve matched the real curve. The last thing we're going to look at is reciprocal graphs. These behave rather differently to any of the polynomial curves. Quadratics, cubics, quartics, quintics, etc. All of those are well defined for any value of x. These curves are not. There will be certain values that break these curves. Now, the 6 examples I've got here are some of the more fundamental types of these. It's possible to have y equals 1 over x plus 7, for instance, in which case the process of substituting in x equals 0 to find a y-intercept or substituting y equals 0 to find an x-intercept will work if there are x or y-intercepts to be found. But in this case, if you try that, you'll find you get no solutions for x-intercepts, for roots of the equation, for points where it crosses the x-axis, and there'll be no solutions for the y-intercepts either. That's a bit of a clue that we're dealing with creatures that involve asymptotes. And we can see what happens as x gets bigger. If you have 1 over x, as x gets larger and larger, y is going to get smaller and smaller. So using what you already understand about how these functions work and using clues from the graphs, I'd like you to see if you can match up each of the 6 equations with the 6 curves on the left. I'd recommend you first try a very quick rough and ready matchup. Go with your gut instinct for each one, and then look more closely and critically at each and see if you can identify anything that helps you to either verify that you've got the correct answer or to show you that you've not yet got the correct answer and see if you can rearrange or find a different one to swap it with that makes more sense. When you're confident that you've found the correct solutions, come back, unpause, and we'll talk through them together. So the very first one that we might recognize straight away, you might remember this one, is y equals 1 over x. This one belongs down here. And the reason I know it must be that one and not one of the others that might look similar, like the two on the right hand side, is that we can see, for instance, it crosses at the point 1, 1, and it's got some lovely symmetry. The point 2, a half is there, and so is the point a half 2. In other words, if y equals 1 over x, then x equals 1 over y. The same curve is its own reflection in the line y equals x. It's its own inverse function, in fact. So if you find the reciprocal of a number, and then you find the reciprocal of that, you'll be back at the original number. The reciprocal of 7 is 7. Now, there are other curves that also have that property. If we look at the top right, for instance, you'll see that that curve is also symmetrical about the line y equals x. However, if you put an input of 1 into that curve, you get an output of 3. So that one is likely to be something more like this. It's related to the y equals 1 over x graph. It's still a self-inverse. If you divide 3 by a number, and then you divide 3 by your answer, you'll get back to your original number. Try it. 3 over 6 is a half, and 3 over a half is 6. So you're back to 6 again. But both of those curves have one thing in common. Y is the same sign as x. If x is positive, then y is also positive, because we're just dividing a positive number by a positive number. If, on the other hand, x is negative, then so is y. And that means we're only expecting the curve to exist in the first or third quadrants. If you're unfamiliar with that way of describing the bits of the graph, let me clue you in. The first quadrant is the one where x and y are both positive. If you move across to the second quadrant, we have a negative value for the x coordinate, but a positive value for the y coordinate. The third quadrant, as we go around anti-clockwise, has negatives for x and y, and the fourth quadrant has a negative y coordinate, but a positive x coordinate. So the typical direction of travel is from the positive x direction around anti-clockwise about the graph. That idea might help us when we get to y equals minus 1 over x, because unlike y equals 1 over x, this one is going to give the exact opposite sign. If x is positive, y is negative, and if x is negative, y is positive. So we get a curve which looks very similar, but is actually a reflection in either of the axes. It doesn't matter which one you think of, a reflection in the x-axis, which is because we've multiplied the function by minus 1, or a reflection in the y-axis because you can think of replacing x with negative x. However you come to that conclusion, we can see points like 2 minus a half, or points like minus 1, 1, that verify for us that this seems to work. Just like the other two we've seen, we've got x and y axes asymptotes, but we can check that as x gets larger, we've got a small negative number for y, and as x becomes lower and lower, y becomes smaller and smaller, but positive. Now, the next three are a bit different. They don't have x on the bottom anymore, they've got something else. 10 over x squared, for instance, has an x squared. Now, whether x is positive or negative, x squared will always be positive, unless x is 0. X can't be 0 here, so x squared will always be positive. And if we divide 10 by a positive number, we get another positive number. So y is always positive when we have 10 over x squared. And that means we can rule out the bottom two curves, and y equals 10 over x squared has got to be this top one. We can then see, if you check some of the numbers, when x is 2, y looks like 2.5. That fits. 10 over 2 squared is 10 over 4. That's 2.5. The symmetry in this graph is not rotational symmetry or symmetry in the line y equals x, but there's mirror symmetry in the y-axis here. And that's because the function we're looking at is known as an even function. Any powers of x that appear are even numbers, and that means that no matter what sign x is, we'll get the same result. So if you look at the y coordinate when x is 3, it'll be the same as the y coordinate when x is minus 3. In both cases, it's a little over 1. It's 10 over 9. The next curve, y equals minus 1 over x squared, will have a very similar pattern to 10 over x squared, but completely flipped over. Because now x squared is never negative, but minus 1 over x squared is never positive. So we're going to be dealing with this graph here. Again, we've got symmetry in the y-axis, and we have the value of y approaching 0 when x gets either very large or very low. And we have a problem when x is 0, so we've got an asymptote hole in the function when x equals 0. But for all other values, we're getting a negative value for y, regardless of what x happens to be. Now the last one is a little bit sneakier, but it's lost some of the symmetry of the, say, 3 over x or minus 1 over x. 1 over x to the 5 is distorted in a different way because x to the 5 makes large numbers much larger, and it makes small numbers, i.e. numbers that are smaller in size than 1, much smaller. So if you look carefully, we know which one this is going to be. If you look carefully, we can see why that makes sense. If we do 1 over 1 to the power 5, we still get 1. So this curve will go through the point 1, 1. And similarly, it'll go through the point minus 1, minus 1. But if we substitute in larger values for x, the curve very rapidly shrinks down. So if we try 2 to the power of 5, that's 32. So the coordinates there will be 2, 1 over 32. The y coordinate is 1 over 32, very small number. Whereas if you try a number that's less than 1, like a half, you'll be doing 1 over a half to the 5, which gives you an answer of 32. So big that it's off the charts on this graph. So a few general principles that you can pick up and learn from these. If you're dealing with a curve which is of the form something over x, then we know it's going to have asymptotes on the x and y axes. We know that it will inhabit the first and third quadrants, just like we saw with 3 over x and 1 over x, whenever k is positive. In other words, if you've got 5 over x or 7 over x or 3.4 over x, then we're dealing with a curve that's going to have one of its branches in the first quadrant where x and y are both positive, and one of its branches in the third quadrant where x and y are both negative. The other alternative is that the curve appears in the second and fourth quadrant, just like with this example over here, y equals minus 1 over x. That happens when you have a negative number on the top of your fraction. Now, if we're looking at curves of the form y equals k over x squared, then we get a slightly different effect. We'll still have asymptotes on the y-axis and the x-axis, but the curve will either be in quadrants 1 and 2, like in this one, and that happens whenever the number on top is positive, or it will be in quadrants 3 and 4, like this one, and that happens whenever the number on the top is negative. Now you should be able to have a go at the questions in exercise 4C. There's only a couple of them, but if you can interpret those and sketch those quickly and easily, then you'll be well placed for moving ahead when we start to look at how we interpret when we're solving two function equations together. We can look at both of their graphs and see where they cross, and when we start looking at graph transformations, we'll be starting from an assumption that we can sketch things like cubics, quadratics, quartics, reciprocal graphs, and then we can move them around. We can think about what happens when they are shifted up or down, when they're stretched either horizontally or vertically, and we should find that then we can sketch a much broader range of functions just by using these functions we've gone through today as our starting point.